Welcome to another deep dive. Today we're going to be looking at this really interesting paper by Gomez, Leos, and Martin.
Okay.
It's all about tiling randomly perturbed bipartite graphs with copies of a specific smaller graph, KIH.
Right.
I think it's a fascinating blend of extremal and random graph theory, and you know, I'm really excited to dig into this with you, especially the proofs.
Yeah.
And you are definitely an expert in this area, so I think we can go pretty deep.
Looking forward to it. It's always a pleasure to kind of delve into the intricacies of graph theory, and this paper offers a particularly rich landscape to explore.
Absolutely. So let's set the scene a little bit. The paper dives into this idea of a threshold. Like, at what point when you add random edges to a bipartite graph do you kind of guarantee a perfect tiling with KAH?
Wow.
And they're specifically looking at bipartite graphs that have a given minimum degree,
Right.
which adds like another layer of complexity.
Yeah, it really does. They're building on these classic questions in extremal graph theory. How sparse can a graph be while still guaranteeing certain substructures?
Right.
But then they introduce randomness, which shifts the whole paradigm.
Right. And so before we jump into like all the theorems and everything, can we just get on the same page with some of the terminology?
Sure.
Like they use the term perfect H tiling and threshold function and epsilon regular pairs.
Right.
Just to make sure we're all on the same page.
Yeah. So a perfect H tiling in this context means we're going to completely cover the bipartite graph with non-overlapping copies of K-chair. Think of it as perfectly fitting tiles together to form a complete mosaic.
Okay, that makes perfect sense. So what about this threshold function?
Yeah.
I mean, it sounds almost like ominous, like a tipping point or something.
It is a tipping point. It describes the minimum density of randomly added edges needed to make a perfect K tiling almost certain.
Mm-hmm.
Below this density, no tiling is possible, but above it, a tiling is very likely to exist. You can think of it like a phase transition in a physical system.
Okay, that's a really good analogy. So the threshold function kind of quantifies that transition from impossible to almost guaranteed.
Exactly.
And then epsilon regular pairs.
Yeah.
That's not kind of technical.
Yeah, epsilon regular pairs are really key to analyzing these graphs. Essentially, they're pairs of vertex sets within our bipartite graph that behave almost like a random bipartite graph. The epsilon measures how close their edge distribution is to true randomness.
Interesting. So we're looking for pockets of like pseudo-randomness within a structured graph.
Exactly.
And this concept ties into the Semirati regularity lemma, which comes up later in the paper.
Exactly.
Right.
The regularity lemma helps us break down the graph into these epsilon regular pairs, making the analysis more manageable.
Okay, got it. So let's kind of dive into the heart of the paper, which is their main result. Theorem 2.
Yeah.
This theorem establishes the precise formula for this threshold function.
Right.
Which is quite a feat.
Yeah. Theorem 2 provides the precise density of random edges needed to guarantee a perfect KH tiling, given the minimum degree of the original bipartite graph.
Okay, so they've given us the formula, but the real meat of it is in the proof, right?
Absolutely.
And they kind of divide that into two major parts. So we've got Theorem 3 and Theorem 4.
Right. Theorem 3 shows that below the threshold, you can't guarantee a perfect tiling.
Okay.
And Theorem 4 demonstrates that above the threshold, a perfect tiling is almost certain given the required minimum degree.
So they're kind of tackling this problem from both sides. They're saying, like, below this, you can't do it. And above this, you can't.
Exactly. We have both necessity and sufficiency.
So let's start with Theorem 3. How do they actually prove that below this threshold, a perfect tiling is impossible?
Okay, so to do that, they construct a very specific bipartite graph, we'll call it G,
Okay.
which cleverly thwarts any attempts at a perfect HHH tiling, even with the addition of random edges below the threshold.
So this construction is really key to kind of understanding the limitations imposed by the threshold. Can you walk us through like the details of this construction?
Absolutely. So picture a bipartite graph, G, with its vertex sets split into 4 parts, A1, A2, B1, and B2.
Okay.
And the sizes of A1 and B1 are carefully chosen to be Ingwen, where W is a constant less than 1 toe ash, and N is the number of vertices.
Okay.
And this leaves 1 win for the sizes of A2 and B2.
Okay, so we've got these 4 groups, and they're carefully sized. And what about the edges? Like, how do they connect these groups?
Right, so here's where the ingenuity lies. They connect every vertex in A1 to every vertex in both B1 and B2.
Okay.
Similarly, every vertex in B1 is connected to every vertex in A2.
Yeah.
But, and this is crucial, there are absolutely no edges between A2 and B2.
Interesting. So we've got these dense connections between certain groups, but like a complete void between A2 and B2.
Exactly.
I can kind of start to see how this might create problems for tiling.
Right. So remember, to tile with KHAs, we need H vertices from each side of the bipartition, all fully connected.
Right.
But because there are no edges between A2 and B2, any attempt to place a KH tile using vertices from A1 or B1 will inevitably fail. You'll always be forced to use at least one vertex from each of A2 and B2, and they just won't connect.
I see. It's like a carefully placed roadblock.
Exactly.
No matter how you try to arrange the KH tiles, you just hit this wall.
Exactly.
But they need to prove that this holds even when you add random edges, right?
That's right. And this is where they employ a probabilistic argument. They leverage lemma 25.
Okay.
Which states that in a random bipartite graph with density below the threshold, the probability of finding a KH tiling covering almost all vertices is incredibly small.
So they're basically saying that even with these random edges sprinkled in, it's very unlikely that you're going to bridge that gap
Exactly.
between A2 and B2 in such a way that you're going to be able to get this perfect tiling.
Precisely.
Yeah.
They've demonstrated that below the threshold, the deterministic constraints outweigh the randomness, making a perfect tiling highly improbable.
Okay, that's really elegant. So they've established the impossibility of a perfect tiling below the threshold. Now let's move on to Theorem 4, which tackles the opposite.
Yeah.
It says above the threshold, a perfect tiling is practically guaranteed.
Right, and this is where the Semirati regularity lemma and the concept of epsilon regular pairs come into play.
Okay.
It's a more intricate proof, but equally fascinating.
Okay, I'm ready for the challenge. Let's go for it.
All right.
But before we jump into all that, let's just take a moment to kind of recap what we've learned so far, and then we can smoothly transition into that proof.
Sounds good. A brief recap will help solidify our understanding before we embark on the next stage of this journey.
For sure.
Okay, so we've established that below this threshold density of random edges, we can't get a perfect tiling.
Right.
Now the question is what happens above that threshold?
Yeah.
And Theorem 4 provides the answer. To prove Theorem 4, they use some pretty heavy machinery. The Semirati regularity lemma.
Okay, yeah. I have to admit that lemma has always been a little intimidating to me.
It is a powerful tool, but it might seem daunting at first. But really at its heart, it's just a way to simplify complex graphs by breaking them down into more manageable pieces. You can think of it like taking a giant, intricate tapestry and dividing it into smaller, more regular patches.
Okay, that's a helpful analogy.
Yeah.
So how does that kind of tapestry dividing work in the context of their proof?
Okay, so they start with a bipartite graph, we'll call it GINA, that meets the minimum degree requirement. Then they apply the Semirati regularity lemma to partition the vertices of GINA into a set of clusters.
Okay, so we're grouping vertices together based on some properties, right?
Right.
But how do we ensure that these clusters are regular in a way that helps us with the tiling problem?
That's where this concept of epsilon regular pairs comes in. The regularity lemma guarantees that most pairs of clusters will be epsilon regular, meaning the edges between them are distributed almost randomly.
So we're creating these like pockets of pseudo-randomness within the graph structure.
Exactly.
And this randomness is kind of key to being able to find the perfect tiling above that threshold.
That's exactly right. Once they have these clusters, they construct what's called the Semirati graph, GSA. The vertices of GSC represent the clusters of GSC. And two vertices in GSCs are connected if the corresponding clusters in GSE form an epsilon regular pair with sufficient density.
So we've created this new graph, GS, and it's kind of like a simplified representation of our original graph.
Right.
Like we've zoomed out to see the overall structure without getting bogged down in all the individual connections.
Exactly. And this simpler representation, GSEs, is what they use to build the K1T tilings.
Right.
Those star-shaped subgraphs that we talked about earlier.
Right, those stars. And they kind of strategically place them across the graph to cover most of the vertices.
Right.
But how do they choose the value of T, the number of arms on each of those stars?
They cleverly choose tilery based on the minimum degree of the original graph, GAS. And here's the key. They use a result called corollary 11, which guarantees the existence of a K1T tiling in GSC that covers almost all of its vertices.
Okay, so corollary 11 is kind of ensuring that we can strategically place these stars to cover most of the graph.
Right.
leaving only a small set of vertices uncovered.
Exactly.
But those leftover vertices are the tricky ones, right?
Yeah, that's right. Those are the tricky ones. How do you deal with those leftovers to complete the perfect tiling?
Right.
And that's where the random edges come in and some really intricate analysis. So what they do is carefully assign these leftover vertices to specific clusters in GSE, making sure that no cluster gets overloaded. And then they leverage the randomness provided by the added edges to create K-ish graphs that incorporate these leftover vertices and connect them to the existing K1T tiling.
So they're essentially using the random edges as like glue to connect the gaps left by that initial K1T tiling. But how do they actually guarantee that this gluing process is going to result in a perfect KHH tiling?
So it's a really delicate process. They do a lot of manipulation of the sizes of clusters in GSE, making them divisible by H, the size of each side of K and HH. They need to make sure that they have the right number of vertices in each cluster to create these complete KHH tiles.
Right. It's like they're arranging all these pieces of a puzzle.
Yes.
And they've got to make sure everything fits perfectly.
Exactly.
And the random edges kind of provide just enough flexibility to make those final connections.
Precisely. It really shows the power of these mathematical tools, the regularity lemma, epsilon regular pairs, the strategic tiling.
Yeah.
And it's a testament to the ingenuity of the mathematicians wielding them.
Right.
By combining these techniques, they prove that above the threshold, with high probability, you can always find a perfect KHH tiling.
That's really impressive. It's like they're saying that a little bit of randomness can actually overcome the limitations of deterministic structure.
Exactly. But they don't stop there. Theorem 5 takes this exploration a step further by examining what happens when we start with a bipartite graph that already has a high minimum degree.
So they're saying, what happens if we start in this high-degree regime?
Yes.
Where the graph is already pretty dense?
That's right.
Does the threshold behavior change?
It does. In the high-degree regime, the threshold for guaranteeing a perfect tiling shifts to a higher density of random edges.
Oh, wow.
It's like the graph is already so well connected that it requires a greater infusion of randomness to make a difference.
That's fascinating. So how do they prove this shift in threshold behavior? Do they use a similar approach to Theorem 3, where they construct a specific graph to show the limitations?
They do, and their construction for Theorem 5 is quite clever. They create a balanced bipartite graph, G, with vertex sets A and B, each split into two parts, A1, A2, and B1, B2, respectively.
Okay, so we're back to dividing these vertex sets into these carefully chosen groups.
Right.
How do they size those groups in this high-degree case?
Okay, so here's the key difference. They make the sizes of A1 and B1 slightly more than half the size of each vertex set.
Okay.
And that leaves A2 and B2 slightly smaller. And this kind of reflects the high minimum degree of the starting graph.
So by making A1 and B1 bigger, they're sort of emphasizing that density of the original graph. But how do they connect these groups to create that roadblock for tiling, like they did in Theorem 3?
Right, so they connect every vertex in A1 to every vertex in B2, and every vertex in A2 to every vertex in B1. But crucially, they leave no edges between A1 and B1 or between A2 and B2.
Oh, I see the pattern. It's similar to that construction for Theorem 3. But the sizes of the groups are different to reflect that high-degree starting point.
Exactly.
How does this impact the tiling problem?
Right, so those larger sizes of A1 and B1 create a constraint.
Okay.
To form a perfect KH tiling, you would need at least one tile that uses more vertices from A1 and B1 than from A2 and B2. But the lack of edges within those groups creates that same bottleneck that we saw earlier.
Right. You're forced to rely on those randomly added edges.
Exactly.
To bridge those gaps.
That's right.
And if the density is below that new higher threshold, it's still very unlikely that you're going to find that perfect tiling.
That's right. They use these probability arguments, similar to Theorem 3, to show that below that new threshold, even finding a single KIH tile that meets these constraints is highly improbable.
So even when you start with this high density of edges, randomness still plays a decisive role.
It does.
It's like there's this constant tension between the structure of the graph and that potential for random connections to open up possibilities.
That is a brilliant observation. This paper really illustrates how those two forces, structure and randomness, interact to shape what's possible in graph theory.
Yeah, it's really neat. It's been fascinating to kind of unpack these proofs and go through all the little details.
It has.
But I have to admit, my brain is getting a little tired.
I understand.
Maybe we should take a break here and let things settle. Before we go on to the final part of our deep dive,
I agree. A moment of pause will allow us to fully appreciate the depth and elegance of the mathematics we've explored so far.
Yeah,
We can return shortly to wrap up our discussion and maybe delve into some of the broader implications of this research.
sounds good.
So welcome back to our deep dive into tiling randomly perturbed bipartite graphs.
Yeah,
We've covered a lot of ground here.
we have.
From the impossibility of perfect tilings below that threshold to the almost certain guarantee above it.
Right.
And we even explored those nuances in the high-degree regime.
Yeah, it's been quite a journey.
It has.
I'm still marveling at how they use these really clever graph constructions
Right.
and these probabilistic arguments to really make their case.
It really shows their deep understanding of both extremal and random graph theory.
Yeah,
And, it kind of speaks to that broader power of combining those two perspectives in math.
absolutely. It's like seeing these two worlds collide
Exactly.
and illuminate each other in really unexpected ways.
Before we wrap up, I think it's worth taking a step back and asking ourselves, what are the broader implications of this research?
Yeah.
What does it tell us about the nature of graphs and this interplay between structure and randomness?
That's a great question.
Mm-hmm.
I mean, it feels like this specific problem, finding these perfect tilings in randomly perturbed bipartite graphs, is just the tip of the iceberg.
Uh-huh.
There must be connections to so many other concepts in graph theory.
Oh, absolutely. For example, the idea of a threshold function, this tipping point where a property suddenly becomes almost certain, appears in many areas of graph theory. Think about things like the emergence of Hamiltonian cycles, or the formation of giant connected components in random graphs, or the existence of specific subgraphs.
Yeah, so this phenomenon where you have this sharp transition
Right.
from unlikely to almost guaranteed, that's a recurring theme.
It is a recurring theme, and understanding these thresholds can give us deep insights into those structural properties of graphs and how they evolve under different conditions.
Yeah, it's like identifying these critical points
Yeah.
where a graph's behavior just changes.
Exactly. And this research also highlights the power of tools like the Semiretti regularity lemma. I mean, it's amazing how they can take this complex graph, break it down into manageable pieces, and then use those pieces to understand these global properties.
It's like imposing order on chaos.
What a great analogy. And, while the regularity lemma might seem abstract and technical, its applications actually go way beyond graph theory. It's used in number theory, computer science, even things like social network analysis.
Wow, I didn't realize it had that broad of an impact.
Yeah, it's like this mathematical Swiss Army knife.
Yeah,
And the techniques that we've talked about in this paper, that interplay between deterministic constructions and probabilistic arguments, have implications for other tiling problems as well. You could explore tilings of different kinds of graphs, you could examine what happens when you change that minimum degree constraint, or even go into the world of hypergraph tilings, where edges can connect more than two vertices.
It's like this paper has opened up so many different avenues for exploration.
That's the beauty of math, isn't it? Every question we answer just leads to more questions. Every theorem we prove opens new doors.
It's been a really fantastic journey diving deep into this paper with you.
The pleasure's all mine.
I feel like I've learned so much.
Good. I hope this deep dive has sparked your curiosity and inspired you to continue exploring.
It definitely has.
Excellent.
Well, until next time, keep those minds sharp and those curiosity engines running. There's a whole universe of knowledge out there waiting to be discovered. Welcome to another deep dive. Today we're going to be looking at this fascinating paper you sent over on tiling randomly perturbed bipartite graphs.
Oh, yeah.
And so this is right up your alley. I know you follow all this cutting-edge research in extremal and random graph theory.
Yeah.
And you've been keeping me updated on all the cool stuff happening with tiling with complete bipartite graphs.
Yeah, Jay.
So we're going to focus on K.
Okay.
Where we have, square vertices on each side.
Yeah.
And so I think what's really cool about this paper is we're really going to get into the weeds of the proofs and, and how they actually show some of these, really surprising results.
Yeah, what's so fascinating about this paper is it really nails down that exact point where you tip over from not being able to tile to being able to tile.
So it's a threshold, right?
Yeah, it's a threshold.
Like how much randomness can you actually add to the graph before you completely lose the ability to find that perfect tiling?
Right, exactly.
So let's jump right into the paper. So they start out talking about embedding problems, which is like a fundamental concept in graph theory.
Yeah, absolutely. I mean, embedding problems are all about finding specific substructures within a larger graph.
Yeah, and we're looking for perfect tilings in this case, right?
Yeah, and in this case, we want to cover all the vertices with copies of KH.
Okay.
And so, there's a bunch of classical results in extremal GF theory about like minimum degree conditions that guarantee certain patterns.
Yeah, like the Karate-Hashno.
Like the Karate-Hashno result.
Which says you need, this minimum degree to force a perfect K3 tiling.
Yeah, so the Karate-Hashno result is a classic example. It says if you have a graph with at least 2n over 3 vertices, and every vertex has degree at least n over 3, then you're guaranteed to be able to perfectly cover the graph with triangles.
Wow.
With K3s.
So if the graph is dense enough and well-connected enough, then we're guaranteed to find this specific tiling pattern.
Yeah.
That's amazing.
That's right.
But then they take us into this realm of random graphs.
Okay.
With the Erdős-Rényi model GNP.
Yeah.
Do you remind us what that is?
So the Erdős-Rényi model is just a way to generate random graphs where each possible edge between two vertices exists with probability p.
Right.
And so you can imagine if you're generating a random graph and p is very small, then you're going to get a very sparse graph.
Right.
And if p is very large, you're going to get a very dense graph.
Right. So p controls the density.
Exactly. P controls the density. And a key question in random graph theory, which is, central to this paper, is to find that threshold probability p at which certain structures almost certainly appear.
It's like how much randomness can we inject into the graph before we lose the ability to find this specific pattern?
Exactly. And they mentioned this really important work by Johansson, Kahn, and Vu, who proved the existence of these threshold functions for perfect H tilings in GMP, where H is strictly balanced.
Okay. And it turns out that KHA fits into that category.
Okay.
But what's really cool is that this paper goes a step further, and it introduces this randomly perturbed graph model.
Okay, so it's a combination of a deterministic graph with a random graph.
Right.
So it's like taking a carefully structured puzzle and then shaking it up a bit.
Right.
Adding some random elements.
Exactly.
How do they define that mathematically?
So they start with this deterministic bipartite graph, denoted by Gn, where ij is a constant between 0 and 1.
Okay.
It represents a proportion of the possible edges.
Okay.
And so this graph has two sets of vertices, A and B, each with n vertices.
Okay.
And the minimum degree of any vertex in the graph is on.
So Kj controls how well connected the initial graph is.
Precisely.
The higher, the denser the initial connections.
Exactly.
Yeah.
And then on top of this, they layer a random bipartite graph, denoted by GNNAP.
Okay.
And so importantly, this random graph only has edges between the two sets, A and B. Okay.
Not within the sets themselves.
Gotcha.
And the P in GN and NP represents the probability that any given edge between A and B exists.
Okay, so the combined graph is like this hybrid.
Yes.
Part carefully planned structure and part random chaos.
Right.
And they're trying to figure out under what conditions can this hybrid graph still be perfectly tiled with KHAH pieces.
Exactly. And there's some really nice previous work by Zhao on minimum degree conditions for perfect AGH tilings in purely deterministic bipartite graphs.
Okay.
And this paper is really building upon that foundation.
Okay, so they're adding in the random element and asking how much randomness can we tolerate while still guaranteeing these perfect tilings.
Exactly.
And so the big question is, what is that threshold function?
Yes.
That probability P.
That precise probability P.
At which we tip from almost certainly not having a perfect tiling to almost certainly having one.
Yeah, and theorem 2 is what answers that. Okay. So they prove that for sufficiently large n and small, the threshold function for the existence of a perfect TH tiling in the combined graph G prime equals Gn, union Gn, and n at A, is P equals n to the power of minus quantity, 2 H minus 1 close quantity over H squared.
Wow, that's a very specific result.
It is. It is.
So what are the broader implications of this?
So I think one of the really interesting implications is that even a small amount of randomness can be enough to disrupt the perfect tiling if the initial graph isn't sufficiently dense.
Okay.
But on the other hand, if we have a bit more initial structure, even a relatively small probability P can lead to a perfect tiling.
Yeah, so it shows this balance, right?
Yeah.
Between structure and randomness.
This delicate balance between structure and randomness.
And it's fascinating that if we start with an empty graph,
Yeah.
meaning TA is 0,
Yeah.
the threshold involves a polylogarithmic factor.
Right.
But in this perturbed setting, even a tiny bit of initial structure makes that factor disappear.
That's right. It suggests that even a small amount of pre-existing structure can make a really big difference in how much randomness a graph can tolerate.
Oh.
And in fact, they connect this to similar phenomena in other perturbed graph problems,
Okay.
like finding Hamiltonian cycles or spanning trees.
So it's not just about this specific tiling problem,
Right.
but this broader principle about structure and randomness.
Exactly.
It feels like we're uncovering some fundamental truth about how networks behave.
Yeah, I totally agree.
And they point out that there's been a lot of interest recently in perturbed graphs,
Yeah.
where Aki is bounded below by a constant.
Right.
So this means the minimum degree of the initial graph is relatively high.
Yes.
So there's already a good amount of structure in place.
Exactly.
It's like starting with a puzzle where a significant portion is already assembled.
Right.
Does their result apply to these cases as well?
Well, so they prove a separate result for the high degree case.
Okay.
And that's theorem 5.
Okay.
And it states that when Aki is very close to 1/2, the threshold probability is at least n to the minus quantity h plus 1 close quantity over h.
Okay.
So you actually need a higher probability
Yeah.
of random edges to guarantee a perfect tiling when you already have a lot of initial structure.
So in a way, randomness can be less helpful.
Yeah, it's almost like the randomness is disrupting the existing structure.
Right, because you're already close.
That was already close to being perfectly tiled.
Yeah.
And actually, they hint at an interesting open question,
Okay.
which is, how does that threshold behave when Ratto is very close to 1/2? So there's still...
A question to ponder.
Yeah, a question to ponder.
Okay, so before we get too far ahead of ourselves, can you give us just a quick overview of how they actually go about proving these results?
Sure, yeah. So they split the proof of theorem 2.
Okay.
Which is, their main result into 2 parts.
Okay.
So first, they have to show that if Chias-Groups is below their stated threshold, then there's at least one graph that won't have a perfect Ka-H tiling even after the random perturbation.
Okay.
So that's theorem 3.
So they're finding like a worst-case scenario graph?
Exactly. A worst-case scenario graph that proves the threshold can't be any lower.
Okay.
And then for the second part, theorem 4, they have to prove that if P is above the threshold, then every possible graph with our minimum degree condition will almost certainly have a perfect tiling after the perturbation.
Okay.
And so this is where they bring in a lot of tools from extremal and random graph theory.
Yeah, it sounds like quite a challenge.
It is.
So before we dive into the proofs themselves, they lay out some preliminary notation and tools.
Right. So they very quickly go through some standard graph notation, like VH, EH, chi of H, and delta of H, to represent the number of vertices, the number of edges, the chromatic number, and the minimum degree of a graph H.
Right, so setting the stage with all the language of graph theory.
Exactly. And then they also define this neighborhood notation for a vertex X.
Okay.
So n of X represents the set of vertices adjacent to X.
Okay.
Dig of X denotes the degree of X.
Okay.
Dig of X, A represents the number of neighbors X has within a set A.
Okay.
And then they clarify this specific notation that they use throughout the paper.
Yeah.
The symbol much less than means sufficiently smaller than.
Okay.
And this helps them express relationships between the various constants.
All right, so they're being very careful about defining their terms.
Nice.
Okay. What other tools do they equip themselves with?
So then they move on to some probabilistic tools.
Okay.
They state Markov's inequality.
Okay.
And they mention the Chernoff bound.
Right. So these are important tools for analyzing random variables.
Exactly. Yeah. And so Markov's inequality provides an upper bound on the probability that a non-negative random variable exceeds a certain value.
Okay.
And the Chernoff bound helps you analyze how much a random variable deviates from its expected value.
Right, so they're building a toolkit of probabilistic techniques.
Right.
Okay.
And then they also state lemma 8, which shows that if you randomly choose a subset from a larger set, the proportion of neighbors a vertex has in that subset is likely to be close to its proportion in the original set.
Okay, so this will come in handy when they're looking at those random edges.
Right.
In the perturbed graph model.
Exactly.
Okay.
And then they talk about tiling in bipartite graphs.
Okay.
And so they first discuss this concept of a critical chromatic number,
Yeah.
denoted by chi sub CR of F,
Okay.
which for a bipartite graph F is the smallest integer t,
Okay.
such that for any positive epsilon, there exists a constant k, such that any graph G with minimum degree, at least 1 minus 1 over t plus epsilon times the number of vertices in G,
Okay.
contains an F tiling covering at least 1 minus epsilon times the number of vertices of G vertices.
Okay. So that's a mouthful.
That's a mouthful, but
Essentially,
this critical chromatic number is telling us how efficiently
Right.
we can tile a graph
But-
with a specific bipartite structure,
Okay.
even if we can't achieve a perfect tiling.
Okay.
And then they bring in Theorem 10,
Okay.
which is a result by Bush and Zhao,
Okay.
which states that for a bipartite graph, F with critical chromatic number
No.
of F equals T greater than or equal to 2,
Okay.
and any positive gamma,
Okay.
if G is a balanced bipartite graph on n vertices with minimum degree at least quantity 1 minus 1 over t plus gamma close quantity times n over 2,
Okay.
then G contains an F tiling,
Ah.
covering at least quantity 1 minus t gamma close quantity times n vertices.
Okay. So this is a powerful theorem that's going to help them
Yes.
guarantee a near perfect tiling.
Exactly.
Yeah.
In a balanced bipartite graph.
Okay.
And then they specialize this theorem
Okay.
to K1 tilings.
Okay. So these star-shaped graphs are coming up everywhere.
Yeah.
Why are they so important in this context?
So they're very important because they allow for a lot of flexibility when you're trying to cover vertices.
Right.
And remember, we're dealing with leftover vertices
Right.
from the Semeredi regularity lemma.
Yeah.
And so those K1T tilings really provide a nice way to incorporate them
Okay.
into a near-perfect tiling.
Gotcha. So they're setting themselves up to handle those leftover vertices efficiently.
Exactly.
Okay. What else do we need before we dive into the proofs?
And finally, they give us a heads up that they'll be using a bipartite version of Semeredi's regularity lemma.
Okay.
And this is, a really powerful tool that allows you to partition a graph into a bounded number of pieces.
Yeah. This lemma is like legendary in graph theory.
It is.
But I'll admit it's still a bit mysterious to me.
Yeah.
Can you shed some light on what it does?
Yeah. So Semeredi's regularity lemma says that any sufficiently large and dense graph can be partitioned into a bounded number of pieces, such that most pairs of these pieces behave almost like random bipartite graphs.
Wow. Okay, so it's like taking a messy, complex network and imposing a kind of order on it.
Yeah, that's a really nice way to put it.
Okay, so they've assembled a whole arsenal of tools from extremal graph theory, random graph theory, probabilistic methods.
Exactly.
I'm really eager to see how they actually deploy these tools to tackle these proofs of their main results.
Me too.
So let's move on to the next section where they introduce this concept of epsilon regular pairs
Oh,
and really dive into the Semeredi's regularity lemma.
sounds good. So we're picking up where we left off, delving deeper into the paper's proof strategy. Remember, we talked about Semeredi's regularity lemma.
Yeah, that powerful tool for partitioning a graph into these well-behaved pieces.
Right. And to really understand how it works, we need to grasp the concept of irregular pairs, which is how they start this section.
Okay, so irregular pairs. This sounds like a way to quantify how predictable or random-like the connections are between different parts of the graph.
Exactly. They start by defining the density, E, x, y, between two sets of vertices, x and y, as just the ratio of edges between them to the total number of possible edges.
So how densely connected they are.
Right. And then a pair of vertex sets, A and B, is called A regular if for any reasonably large subsets within A and B, the density between those subsets is very close to the overall density between A and B.
Okay, so even if we zoom in on specific parts of A and B, the connection patterns are pretty consistent with the overall picture.
Exactly. It's like saying those subsets are representative of the overall connection pattern between the two sets. But sometimes we need a stronger notion of regularity, which is where D superregular pairs come in.
Superregular. Okay, what makes them super?
In a superregular pair, not only do we have that density condition, but we also require that every single vertex in A has a lot of neighbors in B and vice versa.
So it's not just about the sets being well connected overall, but every individual vertex is also actively participating in those connections.
Precisely. And this makes superregular pairs incredibly useful for embedding structures. They mention the slicing lemma, which basically says that if you have a large superregular pair and you slice off a portion of it, the remaining part is still superregular.
So that superregularity is pretty robust.
It is, and then they have this corollary 14, which says if we chop up a superregular pair into smaller equal-sized pieces, most of those pieces will also be superregular.
Okay, so we can divide and conquer while preserving those nice properties.
Right. Then they introduce randomness into the mix with what they call random slicing, lemma 15. If you randomly partition a superregular pair, most of those pieces will still be superregular with high probability.
Wow, so even with randomness thrown in, we can hold on to that superregularity. It seems like they're building up to something here.
They are. They also have lemma 16, which says that inside any regular pair with good density, we can actually find a large superregular pair hiding within it.
So we can always level up from regular to superregular if we need to.
Exactly. And then comes a couple of really crucial results that connect this regularity stuff to the KHH tilings we're after.
Okay, lay it on me.
The first one, the intersection property, lemma 17, is a bit technical, but basically it says that in a regular pair with decent density, if you pick H vertices from one side, they're very likely to have a common neighborhood on the other side that's not too small.
So if we're trying to build a KAH, it means there's a good chance we'll find enough vertices on the other side to connect to.
Right. And this leads to corollary 18, which tells us that these regular pairs with good density actually contain many copies of Ka, so they have those building blocks we need for the KH tilings.
Okay, the pieces are starting to come together. What's the last result before we get to Semirates' regularity lemma?
It's corollary 19, and this one's really important for dealing with leftover vertices. It says that if you have a superregular pair, AB, and a vertex E outside of A, but with lots of connections into A, then you can find a copy of KHA using V, mostly vertices from A, and H vertices from B.
Okay, so it's like saying, even if we have a vertex that doesn't perfectly fit into the initial structure, as long as it has enough connections into a superregular pair, we can still incorporate it into a K-Altatis tile.
Exactly. And now we finally arrive at the big one, Semirates' regularity lemma, which in their notation is lemma 20.
All right, the moment of truth. So how does this lemma actually work in practice?
It essentially says that you can take any large, dense, multipartite graph and partition it into a manageable number of clusters, plus a small leftover set, such that almost all pairs of clusters from different parts of the graph form regular pairs.
So even if the original graph is a tangled mess, we can impose this structure where most of the interactions between these clusters are predictable and well-behaved.
Exactly. It's like creating a simplified map of the graph's structure, focusing on those regular connections.
And then they take the simplified view a step further with what they call the Semirates graph.
Right. They construct this graph GFC, where each vertex represents a cluster, and an edge between two vertices means the corresponding clusters are irregular and have good density.
So it's like a higher level representation of the graph, focusing only on those well-connected clusters.
Precisely. And importantly, lemma 21 tells us that the minimum degree in the Semirates graph is related to the minimum degree in the original graph, so we're not losing too much information when we switch to this simplified view.
Okay, so the high connectivity carries over to the Semirates graph. What do they do with that?
This is where their strategy for finding a perfect KSS tiling really starts to take shape. They use that corollary 11 we talked about earlier, the one about K1T tilings, to find a near-perfect tiling of the Semirates graph with those star graphs.
Okay, so they're tiling that simplified graph with stars, but it's only a near-perfect tiling, right?
Right. Any clusters that don't fit into the star tiling get added to a leftover set V0, and they make sure they have the same number of stars centered in A as in B to maintain that balance.
Okay, strategically placing those stars to set things up for later.
Exactly. And then they very carefully bound the size of that leftover set V0 to make sure it's not too big.
So far, it seems like a pretty standard approach. Where do things start to get tricky?
Well, now they have to figure out what to do with those leftover vertices in V0, and their strategy is really quite clever.
I'm all ears.
They want to use corollary 19, that one about finding KH, using a vertex outside a superregular pair to incorporate each leftover vertex into a KHH tile.
Oh, I see. So the leftover vertex would be that H outside the superregular pair, and they'd use its connections to find a KHAH that includes it.
Exactly. But they have to be careful not to overload any single cluster with too many leftover vertices.
Right, if a cluster gets too crowded, they might run out of edges to make all the KH tiles they need.
Precisely. So they create this auxiliary bipartite graph called J to represent potential assignments of leftover vertices to clusters.
Okay, so J is like a map of where each leftover vertex could potentially fit without causing problems.
Exactly. And they show that J has high minimum degree, meaning each leftover vertex has many potential clusters it could go to. Then they use a greedy algorithm to find a balanced assignment where no cluster gets too many extra vertices.
So they're carefully distributing those leftover vertices, making sure everything stays balanced.
Right. But now they need to make sure they can actually find those K and E H tiles that include the leftover vertices and their assigned clusters.
And that's where they'll need those superregularity properties, right?
You got it. So they use the slicing lemma to make sure the pairs they'll need for corollary 19 are indeed super regular, even after they've removed a few vertices to accommodate those leftover vertices. They also make sure the size of each cluster is divisible by h, which is important for tiling with kh.
It's like they're meticulously preparing the graph, making sure all the pieces are the right size and shape to fit together.
Exactly. And they even use some clever tricks to adjust the sizes of clusters that aren't divisible by h, adding or removing a few kh tiles as needed.
It's amazing how they manage all these details. It's like a delicate balancing act.
It really is. And now we're in the final stages of the proof. They focus on those center clusters, the ones that form the centers of the star tilings, and make sure they're all the same size, divisible by h.
So they're bringing in even more fine-grained control over those central clusters. What about the other clusters, the ones that form the leaves of the stars?
That's where things get really intricate. They need to make all those leaf clusters the same size and still divisible by h. And this involves a multi-step process of pairing up leaf clusters, strategically removing vertices, and carefully adjusting sizes until everything aligns perfectly.
Wow, it sounds incredibly complex.
It is, but it's a beautiful example of how powerful combinatorial reasoning can be. They meticulously work through all these steps, ensuring that in the end, all the clusters have the right size and divisibility properties.
Okay, so the stage is set. They have all these clusters perfectly sized and ready to be tiled. What happens next?
They carefully match up parts of the center clusters to those leaf clusters to create the final tiling. They randomly partition each center cluster into t-equal pieces and each leaf cluster into two carefully sized pieces. Then they use lemma 25 again to find near-perfect tilings between certain parts of the leaf clusters, leaving just the right number of uncovered vertices.
So they're strategically creating gaps in the leaf clusters that are the perfect size to be filled by portions of those center clusters.
Exactly. It's like they're weaving together those initial star tilings and the leftover vertices to create this perfectly seamless KHH tiling.
It's a beautiful image. But they still need to prove that they can actually find those final KHH tiles, right?
Right. They need to make sure those final pairs of vertex sets that will form the KHH tiles are super regular. That's crucial for applying the blow-up lemma.
The blow-up lemma, that powerful tool for embedding complex structures. It all comes down to this.
It does. And they carefully go through the conditions for superregularity, demonstrating that they hold based on all the meticulous work they've done. Once they have that superregularity, they can finally apply the blow-up lemma to triumphantly complete the perfect KHH tiling.
Wow, what a journey. That was a seriously impressive proof, a testament to the power of graph theory and these really creative techniques.
It was quite a ride. But remember, we still have that other result to discuss, Theorem 5, about the threshold for high-degree bipartite graphs. Ready for another challenge?
Absolutely. Bring on the high-degree case.
Okay.
So let's dive into Theorem 5, which deals with those high-degree bipartite graphs where alpha is close to 1/2.
Yeah, this is where things get a little counterintuitive.
Right. It seems like it should be easier to find a perfect tiling when the graph is already so well connected.
You would think so, but it turns out that that high density actually creates some new constraints.
Okay, so how do they approach this in the proof of Theorem 5?
Well, they use a similar approach to Theorem 3,
Okay.
where they construct a specific graph. That shows why the threshold probability has to be higher.
So another carefully crafted worst-case scenario
Exactly.
to show that a lower probability just won't cut it.
Right.
Okay, how does this high-degree extremal graph differ from the one they used in Theorem 3?
So the graph they construct, which they call G star N
Okay.
still has those two vertex classes, A and B,
Yep.
each split into subsets A1, A2, B1, and B2.
Okay.
But the sizes are slightly different.
Okay.
They set the size of A1 and the size of B1 to be the floor of N over 2 plus 1,
Okay.
and the size of A2 and the size of B2 to be the ceiling of N over 2 minus 1.
Okay, so they've created a little imbalance in the sizes of those subsets.
A slight imbalance, yeah. And then the connections are also strategically placed.
Okay.
G star has all possible edges between A1 and B2,
Okay.
all edges between A2 and B1,
Okay.
and no edges within A1, A2, B1, or B2.
So again, we have these two densely connected components,
Right.
but with the crucial separation. Okay, I'm sensing a pattern here.
Yeah.
Strategic density with intentional gaps.
That's a great way to put it.
So now, because the size of A1 plus the size of B1 is strictly larger than the size of A2 plus the size of B2,
Right.
any perfect KH, tiling would require at least one tile to use more vertices from A1 union B1
Yeah.
than from A2 union B2.
That's right.
So at least one tile would need to use H plus 1 vertices from A1 union B1.
Yeah, because of that size imbalance, you can't perfectly match up.
Yeah.
All the vertices from A1 union B1
Right.
with vertices from A2 union B2.
Okay.
So you're forced to have at least one tile that uses
Yeah.
AH plus 1 vertices.
From A1 union B1.
From A1 union B1.
Okay, and this is where the structure of their graph comes into play.
Exactly.
Have a KH tile that uses H plus 1 vertices from A1 union B1.
Right.
You would need either a K2 subgraph or a K1H subgraph.
Within A1 union B1.
Within A1 union B1. Okay, can you remind me what those subgraphs look like?
Sure. Yeah. So a K22 subgraph
Okay.
is just a complete bipartite graph with two vertices in A1 and two vertices in B1.
Right, so like a little square.
A little square.
Okay.
And then a K1H subgraph is a star with one central vertex and H neighbors.
Okay, a mini star.
A mini star.
Okay.
All within either A1 or B1.
Okay, so to have that H plus 1 overlap,
Right.
we need one of these specific structures to form.
To bridge the gap.
Yes, to bridge the gap.
Created by the size imbalance.
Okay.
But here's the problem.
Okay.
There are no edges within A1 or B1
Right.
in that initial graph G star.
Okay.
So we're relying completely on the random edges.
Yeah, to create these
to get
subgraphs.
those subgraphs.
So they've set it up where a perfect tiling hinges on this really unlikely event of the random edges forming these very specific subgraphs.
Exactly. And so they use Markov's inequality
Okay.
to show that the expected number of K22 or K1H subgraphs in A1 union B1 is very small. When P is below that threshold of R to the minus quantity H plus one close quantity over H.
Okay.
And of course, if the expected number of these subgraphs is low,
Yeah.
the probability of having at least one is also low.
So they've shown that with a probability below the threshold, it's highly unlikely we'll find those crucial subgraphs,
Right.
which means no perfect tiling in their external example.
Exactly.
It's like a trap
It's a trap.
for any tiling attempt that relies on a low p-value.
Yeah, that's a great way to think about it.
So this establishes the lower bound on the threshold,
Right.
and they leave the upper bound as an open question.
As an open problem.
So there's still more to explore
A lot more to explore.
in this high-degree territory.
Yeah.
It seems like the interplay of structure and randomness gets even more subtle and complex.
Definitely more nuanced.
When we start with a graph that's already very dense,
Yeah.
well, this has been an incredibly insightful deep dive.
It has been fun.
We've explored this fascinating world of randomly perturbed bipartite graphs. We've learned how the interplay of structure and randomness governs the existence of these perfect KH tilings.
Right.
We've seen how the authors pinpointed those precise threshold probabilities where perfect tiling suddenly becomes possible.
Using all these tools.
Yeah, all these powerful tools from extremal and random graph theory,
Right.
and how they tackled both the low degree and the high degree cases,
Right.
highlighting all these open questions that remain to be explored.
Lots of future research directions.
Yeah, it's a testament to the power of mathematical ingenuity,
Is.
but also a reminder that even in this world of random graphs,
Yeah.
we can find these really elegant patterns,
Right.
and surprising order can emerge.
Exact.
So it makes you wonder what other hidden structures and thresholds
Right.
are out there waiting to be discovered.
I agree.
So a huge thanks to you for guiding us through this paper.
Well, thank you for having me.
And to all our listeners,
Yes.
thanks for joining us on this mathematical adventure.
It's been a pleasure.
Be sure to check out the show notes for links to the paper and other resources. And until next time, Keep exploring the beautiful and surprising world of mathematics.
I will see you then.
Welcome to another deep dive. Today we're going to be looking at tiling randomly perturbed bipartite graphs.
Oh, fun.
Yeah, it's going to be a good one. We have this paper here by Enrique Gomez-Leos and Ryan R. Martin titled Tiling Randomly Perturbed Bipartite Graphs. I think you are going to be the perfect person to help me unpack this.
Wonderful.
Yeah. So first of all, I guess just to get started, maybe you can remind us, what is a bipartite graph?
Sure. So a bipartite graph is one in which the vertices can be split into two sets, and all the edges go between those two sets.
Okay, so there's no edges within a set.
Exactly.
Cool. And then when we talk about tilings,
Yeah.
what exactly are we talking about?
So a tiling is when we're trying to cover the vertices of a graph using copies of some smaller graph, and we want those copies to be vertex-disjoint.
Okay. And in this case, the smaller graph that we're using to tile is going to be a complete bipartite graph.
That's right. It'll be KHMH.
Okay. And what does that notation mean?
So that's a complete bipartite graph with H vertices in each part.
Okay, so it's a very specific kind of bipartite graph where every single possible edge is present.
Exactly.
Got it.
Okay.
Okay, so then this paper is looking at the case where we start with a bipartite graph that has some minimum degree. So meaning that each vertex has at least a certain number of edges coming out of it.
Right.
And then we add some random edges to it. And the goal is to figure out, when can we tile that graph with these KH?
Yeah, and we want to know what's the probability that we can do that.
Oh, cool. So what is the kind of main result of this paper?
Well, the main result is that they found a threshold probability. So if the probability that you add each random edge is above this threshold, then you can always tile the graph with high probability.
Okay.
And if it's below this threshold, then there are graphs which you cannot tile.
So they found a very precise point where it switches from impossible to almost surely possible.
Oh, no, exactly.
That's pretty cool.
Yeah.
So should we get into the details of this paper?
Sure.
Okay. So I guess let's start with the abstract. They're talking about perfect tilings of balanced bipartite graphs. What do each of those terms mean?
So a perfect tiling, Talens, is just what we were discussing before. It means that every vertex is covered by exactly one of the topies of Ka.
Okay.
And a balanced bipartite graph is one where the two sides of the bipartition have the same number of vertices.
Okay, got it. And then they're talking about the randomly perturbed graph model, where you start with this deterministic graph, Gn, and then you add random edges with probability P to get a new graph, GNNP.
Right.
So what are each of those things?
So Guiana is a balanced bipartite graph on two n vertices,
Okay.
where each vertex has degree at least n. So A is like the fraction of the other side that each vertex is adjacent to.
Okay, cool. So then they have this main result, theorem 2, which says that if alpha is a constant between 0 and 1 and h is at least 2, then the threshold probability for the existence of a perfect K tiling in Gn and P is n to the power of minus quantity 2 h minus 1 over h squared. And this is, I mean, that's a very specific function. It's pretty cool that they were able to figure out exactly what that is.
It is. And one interesting thing about that threshold is that there's no polylog factor.
What does that mean? Was a polylog factor?
So a polylog factor is just something that looks like log n to some power.
Okay.
And often when you're studying random graphs, you find thresholds which involve these polylog factors.
Yeah, so this is a bit unusual in that it doesn't have that.
Exactly.
Okay. And then they have this sentence that says, this is a phenomenon observed in other areas of randomly perturbed graph theory. The polylog factor in the threshold for a property in the random graph case disappears in the perturbed case.
Right.
Interesting. So this is like a thing that happens in these randomly perturbed graphs.
Yeah, there are other examples where you see this same phenomenon.
Okay, cool. So then they sort of break up theorem 2 into two parts, theorem 3 and theorem 4. And theorem 3 basically says that if the probability is too small, then there exists a graph with minimum degree, at least ein, that cannot be perfectly tiled with KH.
Exactly. So that's sort of the lower bound on the threshold.
Okay. And then theorem 4 says that if the probability is large enough, then every graph, AIN, can be perfectly tiled with KH.
Right. So that's the upper bound on the threshold.
Okay, great. So that's like the main result of the paper. Yeah, let's see how they prove it.
Okay.
So they start off with some preliminaries. They give us some notation and some tools that they're going to use in the proof. One of the things they mention is Markov's inequality and the Chernoff bound. Can you maybe remind us what those are?
Sure, so Markov's inequality is a way to bound the probability that a random variable is large.
Okay.
And the Chernoff bound is a more precise way to do that when the random variable is a sum of independent random variables.
Okay, cool. And these are pretty standard tools in probability.
Right, they come up all the time.
Okay. So then they talk about epsilon regular pairs, super regular pairs, and something called the slicing lemma. What are all those?
So let's start with an epsilon regular pair. An epsilon regular pair is a pair of sets of vertices where the edges between them behave in a sort of pseudo-random way.
Okay.
More precisely, if you look at any two large subsets of these two sets, the density of edges between them is about the same as the density of edges between the whole sets.
Okay, so it's kind of like saying that the edges are evenly distributed?
Right.
Okay. And then what's a super regular pair?
A superregular pair is an epsilon regular pair where, in addition to the edges being well distributed, each vertex has a lot of neighbors in the other set.
Okay, so it's like even more dense than a regular pair.
Exactly.
Got it. And then what was that slicing lemma you mentioned?
The slicing lemma basically says that if you take a large subset of an epsilon regular pair, then that subset is still epsilon regular, just with a slightly larger epsilon.
Okay, so if you slice off a piece of this nice, well-behaved pair, you still have a nice, well-behaved pair, just maybe not quite as nice.
Exactly.
Got it.
And there's also a random slicing lemma, which is similar but for superregular pairs.
Okay, so if you take a random slice of a superregular pair, it's likely to still be superregular.
Exactly.
Cool. And they also mentioned something called the intersection property.
Right. So the intersection property says that if you have a sufficiently dense epsilon regular pair and you pick any k vertices from one side, then there's a large set of vertices on the other side that are adjacent to all ek of them.
Okay, so it's kind of like saying that there's a lot of overlap in the neighborhoods of these vertices?
Exactly.
Got it. And why are all of these properties important for this problem?
Well, they're all going to be used in the proof of the main theorem. They help us to analyze the structure of the graph and define those K, H, and H tilings.
Okay, cool.
And one of the key tools they use is Semereti's regularity lemma.
Yes. The famous regularity lemma. What does that one tell us?
So the regularity lemma says that any sufficiently large graph can be partitioned into a bounded number of parts, most of which are epsilon regular pairs.
Oh, wow. So it's like taking this big, messy graph and breaking it down into these nice, predictable pieces.
Exactly.
That sounds incredibly useful.
It is. And it allows us to define something called the Semereti graph, where each vertex represents one of those parts, and two vertices are adjacent if the corresponding parts form an epsilon regular pair.
Okay, so it's kind of like a simplified version of the original graph where we've smoothed out all the irregularities.
Right. And they also use something called the superregularization lemma.
What's that one for?
That lemma allows us to make some of those epsilon regular pairs superregular, which is useful for applying the blow-up lemma later on.
Okay, so we're refining those partitions, making them even more well-behaved.
Yeah.
And I'm guessing the blow-up lemma is another one of those powerful tools.
It is. The blow-up lemma is a very powerful tool that lets us embed spanning subgraphs into superregular pairs.
Okay, so we're taking these smaller graphs and fitting them perfectly into those superregular structures.
Exactly. And it's going to be crucial for constructing the tiling in the proof.
That sounds promising. Ready to move on to the next section and see how all these tools come together.
Let's do it.
So we're diving into the proof of Theorem 4. This is where they actually show us how to construct those perfect tilings.
Right. It gets pretty technical, but the main idea is to leverage those tools we talked about, the regularity lemma, the blow-up lemma, and all those properties of epsilon regular and superregular pairs.
So it's a multi-step process. Where do they even begin?
Well, as you might expect, they start by applying Semereti's regularity lemma to that initial graph grunt.
Okay, so they're taking that big, potentially messy graph and breaking it down into those more manageable epsilon regular pairs.
Exactly. And they construct that Semereti graph, remember? It's like a simplified roadmap of the original graph, with each vertex representing one of those regular pieces.
Right, it highlights the key connections. And then what do they do with this Semereti graph?
They start by finding what's called a partial K1T tiling.
A partial K1T tiling. What is that?
It means they're covering a large portion of the graph with these star-shaped subgraphs. Each K1T has one central vertex connected to other vertices, which are called leaves.
Okay, so they're strategically placing these stars on the graph to cover as much ground as possible. But why K1T? Is there a specific reason for using those?
Yes. Remember the minimum degree condition of the original graph? Each vertex has degree at least on Valigan. Well, by choosing T carefully, they can ensure that this minimum degree condition is preserved, even in the Semirati graph.
So each cluster, represented by a vertex in the Semirati graph, has enough connections to accommodate those K1T stars. They're not placing stars where there isn't enough support.
Exactly.
Okay, that makes sense. But I imagine not every vertex gets covered by these stars. What about the leftovers?
That's where things get really clever. They introduce what's called an auxiliary bipartite graph, denoted by J. This graph helps them carefully assign those leftover vertices to clusters in a way that keeps things balanced.
So no cluster gets stuck with way too many extra vertices. They're spreading the wealth. But how do they actually integrate those leftover vertices into the tiling?
Here's where Corollary 19 comes into play. It basically guarantees that they can find copies of KAAAs, those complete bipartite graphs we're aiming for, around those leftover vertices. And these KHH are embedded within those superregular pairs. Remember how we talked about how those superregular pairs are like those nice, dense, well-behaved regions of the graph?
Right, it's like they've prepped the soil, creating these fertile patches where they can plant those KHH and let them flourish.
That's a great analogy. So at this point, they've covered a good portion of the graph with those K1T stars and strategically placed the leftover vertices. What's next?
Well, to get a perfect tiling, every vertex needs to be part of one of those KH units. And I imagine the sizes of those clusters might not be perfectly aligned for that.
You're exactly right. To make everything fit, they need to make sure the size of each cluster is divisible by H, the size of those KH units. And to do that, they're going to use a combination of removing vertices strategically and those randomly added edges.
Oh, that's interesting. So they're using both the deterministic structure they've built and the random edges to fine-tune everything.
Exactly. But they have to be very careful. Remember, those superregular pairs are essential for applying those powerful lemmas, so they need to make sure that removing vertices doesn't mess up the superregularity.
It's a delicate dance.
Yeah.
But I trust they have a plan.
They do. They focus on those center clusters, the ones at the heart of the K1T stars. Using lemma 18, they can carefully remove vertex-disjoint copies of KHH from those center clusters, adjusting their sizes while preserving superregularity.
So they're not just removing random vertices, they're removing entire KHA units strategically. Pretty clever.
It is. Then they move on to the leaf clusters. And here they use a combination of random edges and lemma 25 to adjust their sizes as well.
So they're really using all the tools at their disposal. Deterministic structures, random edges, and all those carefully chosen lemmas.
You got it. And now we're nearing the grand finale.
Okay, lay it on me. How do they bring it all together?
They partition those center clusters, randomly dividing each one into 2 equal parts. And then, using the random edges again, they create a partial tiling between the leaf clusters.
So they're building connections between those leaf clusters, using the randomness to weave them together.
Exactly. And what's amazing is that they're able to prove that whatever vertices remain in those leaf clusters after this partial tiling can be perfectly matched with the corresponding parts of those divided center clusters, forming those final KH edge units.
It's like they've created these puzzle pieces that fit together perfectly, using a combination of careful planning and those serendipitous random edges.
That's a great way to think about it. But wait, there's one more piece to the puzzle, the blow-up lemma. Remember how we talked about how it lets us embed graphs, even if their structures aren't perfectly aligned?
Yeah, it's like the glue that holds it all together.
Exactly. They use the blow-up lemma to make sure that those final KH units are all perfectly connected, creating that beautiful, complete KH tiling.
It's like watching a master architect at work, combining precision engineering with a touch of artistic flair.
I love that analogy. And this proof really highlights the power of combining deterministic and probabilistic methods. It's a beautiful example of how randomness, when used strategically, can actually help us create order and structure.
I'm really impressed. But before we move on to the concluding remarks, I wanted to touch on that detour they took in Section 6 to talk about high-degree bipartite graphs. It seemed like something interesting was going on there.
Right. They briefly explored what happens when the minimum degree of the graph is close to half the number of vertices. So we're in the realm of very dense networks.
So did they find that the same threshold probability applies in those cases?
That's what they investigated. And it turns out things are a bit different in that high-degree regime. They constructed a specific example of a graph that meets the minimum degree requirement, but can't be perfectly tiled unless the probability of those random edges is above a certain threshold. And that threshold is actually higher than the one we discussed for general bipartite graphs.
So counterintuitively, even though these graphs are more densely connected, they actually need a higher probability of random edges to guarantee a perfect tiling.
Exactly. It highlights the complex interplay between the existing structure of the graph, represented by its minimum degree, and the role of those random edges.
Okay, this is getting deep. I'm starting to appreciate the subtle nuances of this problem. Ready to move on to the final part of the deep dive to see what the authors have to say about the implications of all this and what questions remain open.
Let's do it.
Wow, okay, that was quite a journey. So we've seen how Gomez-Leos and Martin prove that there's this precise threshold probability that determines whether we can perfectly tile these randomly perturbed bipartite graphs using those KHA subgraphs.
It really is remarkable, isn't it? They've managed to find that sweet spot where order and randomness come together to create these beautiful tilings.
Right. And it's not just about the result itself. The techniques they use are pretty impressive too. The way they combine those classic tools from graph theory, like Semiretti's regularity lemma, with these sophisticated probabilistic arguments.
Absolutely. It's a really nice example of how these different areas of mathematics can come together to solve these complex problems.
It makes me wonder about other areas where we might be able to use similar approaches. I mean, think about real-world networks like social networks or communication networks.
Oh, definitely. Those networks have an underlying structure, but they're also subject to all sorts of random events and fluctuations.
Right. Like, think about a communication network where nodes can fail randomly. Could we use these ideas to understand how much disruption a network can tolerate before it loses its functionality?
That's a fantastic question, and it goes beyond just robustness. We could potentially use these insights to design more efficient and adaptable networks.
Right. Networks that can reconfigure themselves in response to changing conditions.
Exactly. There's so much potential for applying these ideas to real-world problems.
Okay, so we've talked about the main result and some potential applications. But I'm also really curious about those open questions the authors mentioned. Like, remember how they briefly touched on high-degree bipartite graphs?
Yeah.
I wonder what happens when we push that even further.
Yeah. What if the minimum degree gets even closer to half the number of vertices? Does that threshold probability change again? Do new challenges arise?
And what about going beyond bipartite graphs altogether?
Right. What about multipartite graphs with 3 or more sets of vertices? Could we extend these results to those more general settings?
I mean, they mentioned that there's an analogous result for multipartite graphs, so maybe there's a deeper, more universal principle at play here.
It's definitely worth exploring. It would be amazing to find some kind of fundamental law that governs tiling in all sorts of graphs, regardless of their structure.
That would be incredible. A mathematical equation that captures the balance between order and randomness in these complex systems.
It really highlights how even these seemingly abstract mathematical problems can have these far-reaching implications.
Okay, so as we wrap up this deep dive, what are your final thoughts? What should our listeners take away from this?
I think the biggest takeaway is that the interplay between deterministic structures and random elements is incredibly rich and leads to some really surprising results.
Like the fact that sometimes a bit of randomness can actually help us achieve order and structure.
Exactly. And I think this paper has opened up some really exciting new avenues for research, both in pure mathematics and in its potential applications.
Well said. And for our listeners, if you're interested in learning more, we highly recommend checking out the full paper by Gomez-Leos and Martin. It's a fascinating read.
Absolutely. And who knows, maybe you'll be the one to solve those open questions and push this area of research even further.
That's the beauty of math. It's a never-ending journey of exploration and discovery. So until next time, keep those mathematical minds engaged and keep exploring the amazing world of graph theory. Welcome to another deep dive. Today we're going to be looking at graph theory, specifically a paper by Enrique Gomez-Leos and Ryan R. Martin.
Oh, yeah, I know this paper.
It's called Tiling, Randomly Perturbed Bipartite Graphs.
Yes.
So before we even get into the specifics of their paper, can you just remind everybody about the basics of bipartite graphs and complete bipartite graphs?
Sure. So a bipartite graph is a graph whose vertices can be divided into two disjoint sets, such that no two vertices in the same set are adjacent.
Okay.
So there's no edges between vertices in the same set, only edges between vertices in different sets.
So it's like if you have a classroom of students,
Right.
and you want to split them up into two groups.
Yes.
And so like nobody within a group can talk to each other. They can only talk to the people in the other group.
That's a great way to put it. And then a complete bipartite graph is a bipartite graph where every vertex in one set is adjacent to every vertex in the other set.
Okay, so that's like saying in our classroom, every single student in one group has to talk to every single student in the other group. Okay, cool. So now that we've got the basics out of the way, what are Gomez, Leos, and Martin trying to figure out in this paper?
Well, they're interested in figuring out when you can perfectly tile a bipartite graph with copies of a complete bipartite graph, sub.
Okay, so just so everybody's clear.
Yeah.
When we say sub, that means...
That's the complete bipartite graph where each of the sets has os vertices.
Okay, cool. So basically they're asking, can we cover every single point in our bipartite graph with these little sub game boards?
Exactly. And the catch is that they're adding random edges to the bipartite graph, which makes things a bit more complicated.
Okay, so it's not just like we have this perfectly structured graph. We're actually like throwing in some wrenches.
Yeah, exactly. We're adding a little bit of chaos into the mix and seeing how that affects our ability to tile the graph.
Interesting. So why would they even want to add these random edges in the first place? I mean, doesn't that just make the problem harder?
It does make it harder in some ways, but it also makes it more realistic. I mean, in many real-world networks, you don't have these perfectly structured connections. There's always a bit of randomness involved.
Right, like in social network. Not everyone you know is perfectly connected to everyone else.
Exactly. And so by adding this randomness to the model, they're able to capture a bit more of that real-world complexity.
Okay, that makes sense.
Yeah.
So what's the big takeaway here? Like, what did they actually discover about these randomly perturbed graphs?
Well, one of their key findings is that even a small amount of randomness can make a big difference in whether or not you can perfectly tile a graph.
So like just a little sprinkle of chaos can actually make things work out better.
Yeah, exactly. In some cases, it might even be necessary to have that randomness in order to achieve a perfect tiling.
Wow. That's pretty counterintuitive.
Yeah.
I would thought that more randomness would just make things more messy and harder to control.
It's definitely a surprising result, but that's what makes this paper so interesting. It challenges our intuitions about how randomness affects these kinds of structures.
Okay, so can we get a little bit more specific? Like, how much randomness are we talking about here? Is there some sort of threshold?
Yes, they actually introduce this idea of a minimum degree condition, and then on top of that, they add random edges.
Okay, so what's the minimum degree condition?
So the minimum degree condition basically says that every vertex in the graph has to have at least a certain number of edges connected to it.
Okay, so it's like saying in our classroom example, every student has to know at least like 3 other students in the other group.
Exactly. And that minimum number of connections is what we call the minimum degree.
Okay, I see. So why is this minimum degree condition important?
Well, it's kind of like a starting point. It ensures that the graph is at least somewhat connected to begin with.
Right, because if you had a student who didn't know anybody in the other group, then they wouldn't be able to participate in those sub game boards.
Precisely. So the minimum degree condition is like a basic requirement for tiling to even be possible.
Okay, that makes sense. And then on top of this minimum degree, we're adding some random edges.
Right. And what Gomez, Leas, and Martin found is that if you add enough random edges with a high enough probability, you can overcome certain structural limitations that might prevent you from tiling the graph.
So it's like those random edges are kind of like bridges that can connect different parts of the graph that might otherwise be isolated.
That's a great analogy, and that's one of the key insights of this paper, that randomness can actually help to create more connections and make the graph more tileable.
Okay, so we've got this minimum degree condition, and we're adding random edges, but before they dive into how they prove their main result, they start by giving this really cool example, right? An extremal example to illustrate why just having a high minimum degree isn't always enough.
Yes. This is a really clever example that shows how the structure of the graph can really matter.
Okay, so walk me through this extremal example. What does it look like?
All right, so imagine you take your bipartite graph and you divide each of the 2 sets of vertices into 2 subsets. Let's call them A sub 1 sub, A sub 2 sub, B sub 1 sub, and B sub 2 sub.
So it's like taking our classroom and then dividing each group, the chess players and the checkers players, into like beginners and experts or something.
Exactly. And now here's the catch. In this extremal example, edges only exist between very specific subsets. So let's say chess beginners can only play checkers experts, and chess experts can only play checkers beginners.
Ah, I see. So even if, like, overall everybody knows a decent number of people from the other group,
Right.
there's this bottleneck because, like, you can't have a beginner playing against another beginner or an expert playing against another expert.
Exactly. And that's what makes this example so interesting. Because even though the graph might have a high minimum degree, meaning everyone knows enough people overall, the specific structure of the connections prevents you from forming those perfectly connected coup-sub game boards.
Okay, so it's like having all the right ingredients, but they're not mixed together in the right way.
Exactly. And what this example shows is that even with a decent minimum degree, you might not be able to achieve a perfect tiling unless you add random edges with a high enough probability to kind of break up those bottlenecks.
So the random edges are like adding a little bit of spice to the mix.
I like that analogy. And what Gomez, Leos, and Martin are exploring is how much spice you need to add in order to make the whole dish work.
Okay, so this extremal example really sets the stage by showing how delicate this balance between structure and randomness can be.
Yeah.
But how do they actually go about proving their main result? I mean, they throw around this term Semirides regularity lemma, which sounds pretty intimidating.
Yeah, it's definitely a mouthful,
Yeah.
but it's a really powerful tool in graph theory.
So can we break it down, like, for us mere mortals? What does this lemma actually say?
Well, at a high level, it says that you can take any large enough graph and kind of break it down into smaller, more manageable pieces called clusters. And the connections between these clusters behave in a predictable way, even if the graph as a whole is pretty chaotic.
Okay, so it's like taking a giant messy jigsaw puzzle
Right.
and sorting the pieces into little piles based on their colors or patterns.
Mm.
Even though each individual pile might still be pretty random, the relationships between the piles become more clear.
Exactly. And that's what the regularity lemma allows us to do. It lets us look at the big picture of the graph in a more organized way by focusing on these clusters and how they interact with each other.
So it's like they're taming the chaos by creating these little pockets of order.
Exactly. And this lemma forms the foundation for their proof because it allows them to analyze the structure of the graph in a much more systematic way.
Okay, so they use the regularity lemma to break down the graph into these nice clusters.
Yeah.
But how do they actually find those perfect tilings? They talk about this multi-step process in their Theorem 4, right?
So first, they apply the regularity lemma to divide the graph into those well-behaved clusters.
Okay.
Then they find what's called a partial tiling, which means they use copies of sub to cover as many vertices as possible. But inevitably, there are going to be some leftover vertices that don't fit neatly into those complete bipartite graphs.
So it's like they're filling up the graph with as many game boards as they can, but there might be a few players left standing around without a game.
Exactly. And that's where the next step comes in. They very carefully assign those leftover vertices to the existing clusters, making sure that they have enough potential connections to join the party later on.
So they're not just like randomly shoving those leftover players into any old game. They're strategically finding them a good fit.
Exactly. It's all about making sure that everyone has the potential to be part of a complete bipartite graph.
Okay, so they've got this partial tiling, and they've strategically placed the leftover vertices. Now what?
Now comes the really clever part. They use a technique called super-regularization to beef up the connections between the clusters.
Okay, so they're making sure that the players within each cluster are really well connected to the players in the other clusters.
Precisely. It's like making sure that everyone has plenty of potential opponents to play against.
Okay, and then what's the final step?
The final step is to use a tool called the blow-up lemma.
Okay, another intimidating name. What does this one do?
It basically guarantees that if you have this really well-connected structure with the right kind of connection patterns, you're guaranteed to be able to embed those remaining kuzu subcopies that you need.
So it's like saying if we have enough players all eager to play and we've organized them well into these super regular clusters, then we're guaranteed to be able to find those perfect game board arrangements.
Precisely. It's a mathematical guarantee that everything will fit together perfectly in the end.
That's pretty amazing. So essentially, they've shown that if you have a high enough probability of adding random edges, you can overcome those initial structural obstacles and achieve a perfect tiling.
Exactly, and that's a pretty remarkable result because it suggests that a little bit of randomness can actually be a good thing when it comes to these kinds of graph problems.
This has been a really fascinating deep dive so far. I'm starting to see how this seemingly abstract math problem can actually have implications for understanding real-world networks like social networks or even like transportation networks.
Absolutely. And I think what's really cool about this paper is that it challenges our intuitions about the role of randomness in these kinds of systems. Often we think of randomness as something that creates disorder, but in this case, it actually helps to create order and structure.
Right. It's like adding a little bit of chaos can actually make things more organized in the end.
Exactly. And I think that's a really profound idea that has implications far beyond the world of graph theory.
Okay, so we've covered a lot of ground here, but I'm curious to learn more about how they actually quantify and analyze this randomness they keep talking about.
Well, that's where things get a little bit more technical, but we can definitely delve into that if you're interested.
Absolutely. Let's do it.
Great. So one of the key tools they use is something called Markov's inequality, which is a way of bounding the probability of something extreme happening.
Okay, can you give me an example?
Sure. So let's say, the average height of everyone in a room, Markov's inequality can help you figure out the probability of randomly picking someone who's like twice the average height.
Okay, so it's a way of ruling out those really unlikely scenarios.
Exactly. And they use this tool in their proof to show that certain events are just too improbable to really worry about.
I see. And they also use something called the Chernoff bound, right? What's that all about?
Right, so the Chernoff bound is another powerful tool for bounding probabilities, but it's particularly useful when you're dealing with the sum of a lot of independent random events.
Okay, can you give me an example of that?
Sure, so imagine you flip a coin like 100 times. The Chernoff bound can help you figure out the probability of getting like 75 heads or more.
Okay, so it's like analyzing a bunch of coin flips all at once.
Exactly. And in this paper, they use the Chernoff bound to analyze the overall effect of adding all those random edges to the graph, because each edge is like an independent coin flip.
I see. So it helps them understand how all those little random events can add up to create a big impact on the overall structure of the graph.
Precisely. And it's these kinds of tools that allow them to make really rigorous mathematical arguments about the behavior of these randomly perturbed graphs.
Okay, so they're not just like waving their hands and say, oh, it's probably going to work out.
Yeah.
They're actually using some pretty sophisticated math to back up their claims.
Exactly. They're building a solid mathematical foundation for their results.
But this has been a really insightful deep dive so far. I'm starting to appreciate just how complex and fascinating this problem of tiling randomly perturbed graphs really is.
Me too. And we've only just scratched the surface. There's so much more to explore in this paper.
I'm excited to keep digging in.
Me too. Let's do it. It's pretty amazing how they can take these powerful tools and really nail down some solid results about how these graphs behave when you throw in all that randomness. But they didn't just stop at proving these general results. They also dug deeper into some really specific scenarios, like what happens when the minimum degree of the graph is super high, almost half the number of vertices.
Okay, so in our classroom analogy, that's like saying practically everyone in the class knows almost everyone in the other group. You'd think finding those perfect tilings would be a piece of cake at that point, right?
Yeah.
I mean, there are tons of connections to work with.
You would think so, right? It seems intuitive that the more connections you have, the easier it should be to find those perfect sub arrangements. But that's where things get even more interesting. They actually found that a new kind of obstacle can pop up in these really dense graphs.
Wait a second. So even when the graph is practically bursting with connections, there can still be a roadblock that prevents us from finding a perfect tiling. What does that even look like?
It all comes down to the structure again. Remember how we talked about that extremal example where the connections were bottlenecked even though the overall minimum degree was high? Well, they found another extremal example that specifically pops up when the minimum degree is really high.
Okay, I'm intrigued. Tell me more about this new bottleneck. What does this extremal example look like?
Picture our chess and checkers players again, each divided into beginners and experts. Now, in this new extremal example, all the connections from one subgroup, let's say the chess beginners, go to only one specific subgroup on the other side, like the checkers experts.
Ah, I'm starting to see the problem. So even though there are tons of connections overall, they're super concentrated. It's like everyone's trying to squeeze through the same narrow doorway.
Exactly. And that concentration creates a real problem because even though everyone has a ton of connections, they're not spread out evenly enough to allow for those nice, balanced sub game boards. Each of those boards needs an equal number of vertices from each side.
Right. It's like we might have a whole bunch of eager chess beginners ready to play, But there just aren't enough checkers experts to go around. Everyone's stuck waiting for their turn.
Precisely. And what's really fascinating is that this new extremal example shows that you actually need a higher probability of adding random edges to guarantee a perfect tiling in these super dense graphs compared to less dense ones.
That's really counterintuitive. I would have thought that the denser the graph, the easier it would be to tile because you have more connections to work with.
It's a common misconception, but this example highlights the subtle dance between structure and randomness. It's not just about the sheer number of connections, it's about how they're distributed.
Okay, so it's not just about quantity. It's about quality, too. The connections need to be spread out in a balanced way to make those sub-game boards work.
Exactly. And what Gomez, Leos, and Martin are exploring is how much randomness you need to sprinkle in to achieve that balance.
This is starting to remind me of those real-world networks we talked about earlier. Like in a social network, if everyone is super connected, but only within their own little clique, it can actually hinder the spread of new ideas. It's like everyone's trapped in their own echo chamber.
That's a brilliant analogy. It's as if you have a room full of brilliant minds, but they're all talking to the same people and hearing the same things. A bit of randomness, those connections that bridge different groups, can really shake things up and lead to new breakthroughs.
So maybe Gomez, Leos, and Martin have stumbled onto something bigger than just a graph theory problem. Maybe they've uncovered a fundamental principle about how complex systems work. This balance between structure and randomness seems crucial.
I think you're onto something there. It's a reminder that sometimes a little bit of chaos can be the key to unlocking greater order and innovation.
All right, so we've seen how this new extremal example throws a wrench into things even when the minimum degree is super high. But how do they actually analyze and quantify all this randomness they keep talking about? I mean, they throw around terms like Markov's inequality and the Chernoff bound, which sound pretty intimidating.
They do sound a bit scary, right? But these are just tools that mathematicians use to get a handle on random events. Remember, we're dealing with probabilities here, adding edges with a certain likelihood. These tools help us analyze the odds of certain outcomes.
So instead of just saying something like, oh, it'll probably work out, they can actually calculate the likelihood of specific things happening.
Exactly. That's the beauty of math. It lets you be precise about uncertainty.
Okay, so tell me more about Markov's inequality. What does that one do?
Markov's inequality is all about setting boundaries. It helps us determine the maximum probability of an event that deviates significantly from the average. Imagine, the average height of everyone in a room. Markov's inequality tells you how likely it is to randomly pick someone who's way taller or shorter than that average.
Okay, so it's like saying, all right, even though we're dealing with randomness, we can still rule out some extreme scenarios.
Exactly. It's about putting limits on the chaos.
And what about the Chernoff bound? What does that one do?
The Chernoff bound is particularly handy when you're looking at the combined effect of many independent random events. It's like flipping a coin 100 times and wanting to know how likely it is to get a specific number of heads. The Chernoff bound gives you a way to calculate that probability.
So in the context of this paper, it's like they're analyzing the impact of adding all those random edges. Each edge is like a coin flip, and they're looking at the overall result.
Precisely. They're using the Chernoff bound to understand how those individual random events collectively influence the tiling process.
So it's like they're taking all those little coin flips and figuring out how they add up to create the big picture?
That's a great way to put it. These tools allow them to go from individual random events to understanding the overall behavior of the system.
Okay, so they're not just making educated guesses. They're building a solid mathematical framework to analyze the impact of randomness.
Absolutely. They're bringing rigor and precision to the study of these complex systems.
This is all starting to make more sense now. It's fascinating how they combine these powerful tools from graph theory and probability to tackle this problem.
It's a beautiful example of how different areas of math can come together to shed light on complex phenomena.
It's been a really insightful deep dive so far.
Yeah.
I'm starting to see how this seemingly abstract math problem can actually have implications for understanding real-world networks like social networks or even like transportation networks.
Absolutely. And I think what's really cool about this paper is that it challenges our intuitions about the role of randomness in these kinds of systems. Often we think of randomness as something that creates disorder, but in this case, it actually helps to create order and structure.
Right. It's like adding a little bit of chaos can actually make things more organized in the end.
Exactly. And I think that's a really profound idea that has implications far beyond the world of graph theory.
Okay, so we've covered a lot of ground here, but I'm curious to learn more about how they actually quantify and analyze this randomness they keep talking about.
Well, that's where things get a little bit more technical, but we can definitely delve into that if you're interested.
Absolutely. Let's do it.
Great. So one of the key tools they use is something called Markov's inequality, which is a way of bounding the probability of something extreme happening.
Okay, can you give me an example?
Sure. So let's say, the average height of everyone in a room, Markov's inequality, can help you figure out the probability of randomly picking someone who's like twice the average height.
Okay, so it's a way of ruling out those really unlikely scenarios.
Exactly. And they use this tool in their proof to show that certain events are just too improbable to really worry about.
I see. And they also use something called the Chernoff bound, right? What's that all about?
Right. So the Chernoff bound is another powerful tool for bounding probabilities, but it's particularly useful when you're dealing with the sum of a lot of independent random events.
Okay, can you give me an example of that?
Sure. So imagine you flip a coin like 100 times. The Chernoff bound can help you figure out the probability of getting like 75 heads or more.
Okay, so it's like analyzing a bunch of coin flips all at once.
Exactly. And in this paper, they use the Chernoff bound to analyze the overall effect of adding all those random edges to the graph, because each edge is like an independent coin flip.
I see. So it helps them understand how all those little random events can add up to create a big impact on the overall structure of the graph.
Precisely. And it's these kinds of tools that allow them to make really rigorous mathematical arguments about the behavior of these randomly perturbed graphs.
Okay, so they're not just like waving their hands and saying, oh, it's probably going to work out. They're actually using some pretty sophisticated math to back up their claims.
Exactly. They're building a solid mathematical foundation for their results.
Well, this has been a really insightful deep dive so far. I'm starting to appreciate just how complex and fascinating this problem of tiling randomly perturbed graphs really is.
Me too. And we've only just scratched the surface. There's so much more to explore in this paper.
I'm excited to keep digging in.
Me too. Let's do it.
Okay, so we've explored this fascinating world of randomly perturbed graphs, and we've seen how those random edges can shake things up. But one thing that's been bugging me is what happens when you fix the probability of adding those random edges? Like, what if we don't have complete control over how much randomness gets thrown in?
It's a great question. And that's actually one of the things that Gomez-Leos and Martin address in their paper. They look at the scenario where you fix that probability. Let's call it P.
Okay, so P is like the amount of spice we're adding to our graph recipe, and it's staying constant.
Exactly. And what they show in their Theorem 31 is that even when Clece is fixed, you can still achieve a perfect tiling with those Kusub sub-game boards as long as the original graph has a high enough minimum degree.
Okay, so even with a predetermined dose of randomness, we can still make things work if we start with a solid foundation.
Exactly. It's all about having enough initial connections to build upon.
But how high does that minimum degree need to be? Did they actually figure that out?
They did. They were able to pinpoint the exact minimum degree needed for this to work. They call it D sub 0 sub.
So D sub 0 sub is like the magic number. If everyone in our classroom knows at least D sub 0 sub people from the other group, and we add random connections with our fixed probability P, then we're good to go. We can tile that graph.
That's exactly right. It's like they found the tipping point where structure and randomness come together to guarantee a perfect tiling.
That's pretty amazing. I mean, it's not just about having enough connections or enough randomness. It's about finding that sweet spot where they work in harmony.
Absolutely. And that threshold D sub 0 sub is really important because it gives us a concrete understanding of how these two forces interact.
This is really making me think about how randomness plays a role in so many different areas of life. I mean, you see it in nature and social systems, even in the economy. It's like this underlying force that's always at play.
I agree. And I think one of the big takeaways from this paper is that randomness isn't always a bad thing. Sometimes it can actually be beneficial, even essential for achieving certain outcomes.
Right? It's like that old saying, a little bit of chaos is a good thing.
Exactly. And I think Gomez-Leos and Martin have provided some really compelling mathematical evidence to support that idea.
Well, this deep dive has certainly challenged my thinking about randomness and how it can shape complex systems. It's been a real eye-opener.
I'm glad to hear that. And we've only scratched the surface of this paper. There's so much more to explore, and I'm sure we could keep talking about this for hours.
I know. I feel like we've just begun to unpack the implications of their work.
Definitely. But for now, I think we've given our listeners a good taste of the fascinating world of tiling randomly perturbed bipartite graphs. And hopefully we've inspired them to learn more about the power of randomness in shaping the world around us.
Absolutely. Thanks for joining us on this incredible journey into the heart of graph theory. It's been a real pleasure.
The pleasure was all mine.
And to all our listeners out there, Keep those minds curious and those questions coming. We'll be back soon with another deep dive into the world of science and mathematics. Welcome back, everyone, to the Deep Dive. Today, we're going to be diving into something pretty fascinating. A paper, actually. It's called Tiling Randomly Perturbed Bipartite Graphs.
Yeah, it's a mouthful, isn't it?
Definitely a mouthful. But it's a super interesting area of research in graph theory. So before we get lost in the weeds here, let's set the stage a bit. What exactly is a bipartite graph?
Sure. So a bipartite graph, it's basically a graph where you've got two sets of vertices, right? And you can only connect vertices from different sets, so no connections within the same set.
Okay, so like two teams, and the edges can only connect players from opposing teams. Makes sense. And what about tiling? What does that mean in this context?
So tiling, it's like you're trying to cover all the vertices of this bipartite graph, and you're doing it with these smaller, non-overlapping bipartite graphs, kind of like fitting puzzle pieces together.
Got it. So like our puzzle pieces are these smaller bipartite graphs.
Yeah.
And the challenge is figuring out when we can achieve a perfect tiling, right? Where every vertex is covered.
Exactly. And to make things even more interesting, we're throwing in some randomness into the mix.
Ah, yeah, that's where the perturbed part comes in.
Precisely. So we start with a bipartite graph, right? It might have some initial structure, some connections already, and then we randomly add edges between vertices in the two sets. It's like introducing some chaos into the game.
I like that. A bit of chaos. So the big question is, how much randomness do we actually need to make these tilings, these perfect tilings, possible?
Well, that's exactly what this paper by Enrique Gomez-Leos and Ryan Martin explores. They're looking for this threshold, this point where adding enough random edges suddenly makes tiling almost certain.
Okay, that makes sense. And they're focusing on tiling with a specific type of bipartite graph, right? Called complete bipartite graph, or KHA.
Yep, that's right.
So what makes a complete bipartite graph so special? What does it look like?
Well, think about it this way. You've got H vertices in one set and H vertices in the other. And every single vertex in the first set is connected to every single vertex in the second set.
Oh, so it's like a super connected two-team setup.
Exactly. So the researchers are trying to figure out exactly when adding enough random edges will let us perfectly tile our bigger graph using these KHE graphs. It's kind of like finding the sweet spot for chaos, right?
I love that, the sweet spot for chaos. All right, so let's zoom out a little bit and talk about the bigger picture. The paper starts off by talking about something called embedding problems.
Right. Embedding problems are basically about finding these smaller graphs or subgraphs within larger graphs. It's a fundamental concept in graph theory.
Okay, so it's like we're searching for patterns within patterns.
Yeah, kind of. And a big part of research in this area is finding conditions that guarantee that these specific subgraphs exist within these larger graphs. And this is important for both deterministic graphs, those with specific properties, and random graphs where things are, well, more random.
Got it. So there's this interplay between order and randomness. Now, the paper also mentions a classic result from what's called extremal graph theory, the Karate-Hudgenel theorem.
Yeah.
What's that all about?
So, the Karate-Hudgenel theorem, it's a beautiful example of how certain conditions, like having a high enough minimum degree, meaning each vertex has enough connections, can guarantee that we can find specific subgraphs. In this case, a perfect tiling with triangles.
Okay, so more edges, more likely to find those triangles fitting in perfectly. That makes sense. But then the paper takes us into the world of random graphs, where things get, well, a bit more unpredictable, right?
Absolutely. In a random graph, the edges are basically added with a certain probability, like flipping a coin for each possible connection. And there's this really cool result by Johansson, Kahn, and Vu, who actually figured out the exact threshold for perfect tiling in these random graphs. They figured out exactly when we can tile these random graphs with all sorts of different puzzle pieces.
Wow, so they cracked the code for random graphs. Pretty impressive.
Yeah.
So how do these randomly perturbed graphs we're talking about fit into all of this?
They're kind of like a hybrid. Imagine you start with a base graph, maybe something with some structure, like our bipartite graphs, but then you sprinkle in some randomness, adding those random edges.
Right, so it's like a blend of deterministic and random elements, a bit of order and a bit of chaos.
Exactly. And there's been some really interesting work done in this area. Ballo, Triglone, and Wagner, they've made a lot of progress understanding when perfect tilings pop up in these kinds of graphs.
So it seems like finding these tiling thresholds is a recurring theme across different types of graphs.
Definitely. And now we're ready to zero in on the specific problem that Gomez-Leos and Martin tackle in their paper, tiling a randomly perturbed bipartite graph with those KHH graphs, those complete bipartite graphs we talked about earlier.
Right, so our puzzle pieces are those superconnected two-team graphs. And remember, we're only adding those random edges between the two sets of our bipartite graph. No connections within the same set.
Exactly. And before we even bring in randomness, there's some groundwork laid out. There's a result by Bush and Zhao, who looked at tiling balanced bipartite graphs with K-graphs, but without any of the random perturbation.
Okay, so they set a baseline, in a way. They figured out what works in a purely deterministic setting. But how do we even define a threshold when we start adding those random edges? How do we measure that?
That's where the concept of a threshold function comes in. It basically tells us, below this threshold, it's unlikely we'll get a perfect tiling, but above it, tiling becomes much more likely.
It's like we're searching for that tipping point.
Exactly. And finding this threshold function, that's the heart of what Gomez-Leos and Martin's paper is all about. They actually managed to pin it down.
Okay, I'm on the edge of my seat. What is this magical threshold function?
All right, drum roll, please. It's Nolan 2SE.
Whoa, that's a mouthful.
Yeah, it's a bit of a beast.
Yeah.
But basically, n is the number of vertices on each side of our bipartite graph. And as you remember, that's the size of our KH puzzle pieces.
Right, the size of those superconnected two-team graphs. So this function gives us the exact probability of adding random edges that we need to hit in order to make tiling almost certain.
Exactly. And there's a little detail here. This threshold actually works for a specific range of something called ISIS. It represents the initial connectedness of the graph. So the starting graph needs to have a certain level of connectivity for this threshold to work.
So there's a bit of a starting requirement, a bit of a foundation we need. Makes sense. But how in the world did they prove this? I mean, it seems pretty complicated.
They broke the proof down into two parts. Theorem 3, that's the first part, shows us that this threshold is absolutely necessary. If the probability of adding edges is below that value, there will be cases where we just can't get a perfect tiling no matter what.
Okay, so it establishes a lower bound. But what about the other side of things? How do they prove it's also sufficient? That if we're above the threshold, we're good to go?
That's where Theorem 4 comes in. It basically proves that if we're above that threshold, we can almost always get a perfect tiling, no matter what our starting bipartite graph looks like.
Oh, cool. So they've established an upper bound. They've sandwiched that sweet spot.
Exactly. But there's also this interesting thing they talk about, polylog factors.
Oh, yeah. I was wondering about that. What are those all about?
Well, you see, if we were starting with a completely empty graph, meaning absolutely no connections between our two teams at the beginning, the threshold function would need a little tweak, a little boost in the form of this polylog factor. But here's the cool part. In the perturbed case, in the scenario we're focusing on, this factor just vanishes.
So a bit of pre-existing structure simplifies things.
Exactly. It seems like starting with a bit of order actually helps us out in this case.
Fascinating. And for those who like to dig even deeper, they even have a Theorem 5, right?
Yep. That one dives into what happens when we have bipartite graphs with even higher minimum degrees, so even more initial connections. It seems like we might have a different, maybe even higher threshold at play in those scenarios.
So the more connected the base graph, the more randomness we might need to guarantee that tiling. That's an interesting twist. I'm already sensing how complex this research gets.
Oh yeah, it's definitely a deep rabbit hole. And underpinning a lot of this work is a super powerful tool called Semerati's regularity lemma. The authors use it extensively in their proofs.
We've heard that name mentioned a few times. What does this lemma actually do? I mean, can we break it down in simpler terms?
It's a bit technical to explain in detail, but think about it this way. It allows us to take a really complex graph and kind of break it down into these smaller, more manageable pieces that are easier to analyze and work with.
Okay, so it's like a simplification tool.
Exactly. And it helps reveal these hidden patterns within these complex graphs, patterns that would be really hard to see otherwise.
I'm starting to get a sense of how powerful this lemma is.
It's used all over graph theory. It's a real workhorse.
Well, I'm definitely eager to see how they use it in this paper, especially in the proof of Theorem 3. I mean, they actually had to construct this specific bipartite graph, almost like a worst-case scenario, to show why that threshold is absolutely essential.
Right. It's a really clever way to prove a point, to show that if you're below that threshold, you're going to run into trouble.
All right, I'm ready. Lead the way. Let's unpack that proof.
All right, so let's dig into this extremal example, this kind of worst-case scenario graph they cooked up. They call it Jean. It's designed to be really hard to tile with those K graphs unless we add enough random edges.
Okay, so it's like our ultimate test, like an obstacle course for tiling.
Exactly. So we start with our two teams, A and B, each with N players. But each team is then split into two smaller groups. So Team A has subgroups A1 and A2, and Team B, it's got B1 and B2.
Got it. So 4 groups of players now.
Uh-huh.
How do they connect or not connect in this graph?
Well, that's where the minimum degree proportion, that ah, comes in. Remember, I tells us how connected our graph is initially.
Right, higher I means more edges to start with. So how does that play into this construction?
Well, the sizes of these subgroups are carefully chosen based on ah. A1 and B1, they each have on players, while A2 and B2 have new players, where ah is just one R.
Okay, so the relative sizes depend on that initial connectedness. What about the edges? How are these groups actually connected?
Okay, here's the clever part. The graph has all possible edges between A1 and B1, A1 and B2, and A2 and B1, but there are absolutely no edges between A2 and B2.
Wait, so A2 and B2 are completely isolated from each other. That's interesting. Seems like it's done on purpose.
It is. It creates sort of bottleneck, a challenge, if you will, for tiling with K graphs.
Oh.
Unless we add enough random edges to connect A2 and B2.
Ah, okay, I see. So we're trying to show that if the probability of adding random edges, that p-value is too low, we might not be able to get a perfect tiling. How does this graph help us prove that?
Well, let's think about the sizes of these subgroups. The way it's set up, when A is less than 1 i's, it means A, or 1i, is greater than 2ap1. What this means is that A2 and B2 combined actually have more players than A1 and B1 combined.
Okay, so we have these 2 large disconnected subgroups, but each K-graph we want to use for tiling, it needs the same number of players from both teams, right?
Exactly. So to cover all the players in A2 and B2, we would need at least one K-graph that's using players mostly from those subgroups. But because they're not connected initially, the only way to make such a K-graph is if we get lucky and those random edges happen to connect them.
I see. It all comes down to those random edges bridging the gap. If the probability is too low, it's like trying to win the lottery.
Yeah, pretty much. The authors actually use a specific result, lemma 25, which deals with the probability of finding large partial tilings in random bipartite graphs. And they show that if p is on the order of now 2 or less, it's very unlikely we'll get enough K-graphs forming within A2 and B2 to cover all those players.
So no matter what we do, we'll end up with some uncovered players in A2 and B2. That's a really clever way to show that we need that threshold value for P.
Right. It highlights how important that balance is between the initial structure and the randomness we add.
This graph really drives the point home. But Theorem 3, that's just half the story, right?
Yeah.
We still need Theorem 4 to show that if we're above that threshold, we actually can get a perfect tiling, no matter what our starting graph looks like.
You got it. And to prove that, things get a bit more intense, mathematically speaking. They use this whole arsenal of tools, Semereti's regularity lemma, the idea of superregularity, and something called the blow-up lemma, plus a bunch of clever probability arguments.
Ooh, okay. Sounds a little intimidating, but also super exciting. Where do we even begin with something like that?
Well, the first step is to bring in Semereti's regularity lemma. Remember that one? It helps us break down those massive, complex graphs into smaller, bite-sized pieces. It's like using a magnifying glass to see the fine details.
Right, kind of like organizing a giant library into smaller sections with similar books grouped together. But how do we apply it to our tiling problem?
Well, we apply it to our starting bipartite graph, which we'll call Jna. And this lemma guarantees that we can partition the vertices into these clusters, and most of the pairs of clusters will have this special property called arregularity.
Okay, remind me, what's arregularity again?
Basically, it means the edges between those two clusters are kind of evenly distributed, almost like they were connected randomly. It's a way to quantify how random or uniform those connections are.
So it's measuring how well behaved those connections are. Why is that important for our tiling problem?
Because we're going to use these clusters to build a new graph called the Semereti graph. We'll call it GSSE. Think of it like a simplified version of our original graph, a summary, if you will.
Oh, that's interesting. So how do we build this new graph?
Well, each vertex in GSE represents one of those regular clusters from our original graph. And we connect two vertices in GSE if their corresponding clusters back in the original graph are an or regular pair, and they have a density, a proportion of edges, above a certain threshold, which we'll call D.
So we're cherry-picking the well-connected pairs, the ones that have a lot of edges between them. It's like we're filtering out the noise and focusing on the strong connections. What about the minimum degree, that on-rank from our original graph? Does it play a role in this new graph?
Absolutely. That's where lemma 21 steps in. It basically says that the minimum degree property from our original graph, it kind of carries over, at least partially, to this new summary graph.
So our simplified graph still keeps some of that initial connectedness. Makes sense. But how do we actually use this new graph to tile our original graph with those KH graphs?
Okay, here's where things get really interesting. We're going to tile this summary graph, but not with K graphs directly. We're going to use a different structure. K1T stars.
Wait, stars. Those graphs that look like a central vertex with arms coming out? What's the strategy here?
It's a clever move, trust me. We choose to be a specific value based on GS, and using that, along with another result called corollary 11, we can guarantee that we can find a partial tiling of GSs using these K1T stars. And this tiling will cover almost all the vertices in GSs.
Okay, I'm intrigued. So we've almost completely tiled our summary graph with stars. What about the vertices that are left uncovered? What happens to them?
Don't worry, we'll take care of them. We're going to use those random edges, remember? They'll play a crucial role in incorporating those leftover vertices and ultimately getting us that perfect K-esh tiling in our original graph.
Okay, starting to see the bigger picture now. So these star tilings, they're like a foundation, and we'll use randomness to fill in the gaps and get everything perfectly tiled with KS graphs.
Exactly. But the specifics of how we actually do that are pretty intricate. We need to carefully assign those leftover vertices, make sure we have enough connections, and do a bit of fine-tuning to make everything fit perfectly.
Sounds like there are a lot of moving parts. Can you walk us through those next steps? Maybe focus on the main ideas without getting too lost in the technical details.
Of course. Let's break it down. So we've used Semiretti's regularity lemma to break down our graph, right? And we've strategically tiled our Semiretti graph using these K1T stars. Now, we got to deal with those leftover vertices. And this is where the randomness we added earlier, those random edges, really come into play.
It's like we're in the end game now, but I have a feeling there are still some tricky maneuvers ahead.
Oh, absolutely. So think about it this way. Each of those leftover vertices needs a home. They need to be incorporated into one of those K1T stars we created. We'll basically pair each leftover vertex with one of the clusters in the Semiretti graph, a cluster that's already part of a star.
So each leftover vertex gets, like, adopted by a cluster.
Yeah, you could say that, but we can't just randomly assign them. We need to make sure each leftover vertex has enough connections, enough edges to the cluster it's being assigned to. Specifically, at least DL connections, where L is the number of leftover vertices. This ensures that we can actually incorporate that leftover vertex into a K-region tiling later on.
Got it. So enough connections to actually make it work. But couldn't some clusters end up with too many of these leftover vertices?
That's a good point. And that's where fact 26 comes in. It guarantees that we can assign these leftover vertices in a balanced way so no single cluster gets overloaded. It's like a careful foster care system for our vertices, making sure everyone gets a fair chance.
Interesting. So we're spreading the responsibility around. But how do those random edges we added way back when actually help incorporate these adopted vertices into those KH graphs?
Well, that's where corollary 19 steps in. It gives us the conditions that basically guarantee that, given a leftover vertex and a cluster it's connected to, we can find enough other vertices within nearby clusters to actually form a complete KHH graph.
So the random edges are creating those extra connections we need. It's like using those random threads to stitch everything together.
Exactly. But there's still a bit of tailoring we need to do. At this point, we've got those leftover vertices kind of incorporated into KH graphs. But the sizes of our clusters might not be perfectly balanced to get a perfect tiling. Remember, each KH graph needs H vertices from each side. Things need to line up just right.
Right. Got to make everything fit perfectly. So how do we adjust those cluster sizes if they're a bit off?
It's like tailoring a suit. We need to make sure that the number of vertices in each cluster is divisible by H, and also that certain clusters within those stars, clusters that play similar roles, they need to have the same size. To do this, we carefully remove a small number of vertices, again using corollary 19 and lemma 25. We do it in a way that doesn't mess up that irregularity too much.
So we're trimming things down, making those clusters the perfect size. Seems pretty delicate.
It is, and we also need to make sure that the central clusters within each of those K1T stars, they're all the same size, a size divisible by HT. If needed, we strategically remove a few complete KHH graphs to make that happen.
Okay, so we're optimizing those central hubs within our star formations. What's the final step? How do we actually achieve that perfect tiling?
We take each of those central clusters and we partition it into t-equal parts. Each part will be matched with one of the t-leaf clusters in its star. And then we use lemma 25 one last time to find large partial tilings between pairs of those leaf clusters. This leaves just the right number of vertices uncovered in each leaf cluster, the perfect number to match up with one of those portions of the central cluster.
Wow, it's like we're solving a bunch of mini tiling puzzles within the bigger puzzle. Each portion of that central cluster needs to find its perfect match among the remaining vertices in its assigned leaf cluster. And once we do that for all of them, we have our perfect to gauge HH tiling.
Exactly. We've shown that if the probability of those random edges, that PA value, is above our threshold, a perfect tiling is almost always possible, no matter what our starting bipartite graph looks like.
That was quite a journey. We've gone from breaking down this complex graph into these manageable pieces to carefully tiling with stars, assigning those leftover vertices, and then finally using those random edges to make everything fit perfectly. It really shows how powerful it can be to combine those deterministic and probabilistic approaches.
It really highlights the elegance of this whole area of research, and the fact that this threshold function works no matter what our starting graph looks like. It's pretty remarkable. It's like a mathematical guarantee.
Yeah, it's mind-blowing. But before we wrap things up, I gotta ask, what if we changed our puzzle piece? What if we weren't using KH graphs, but something else? Would that change this magical threshold we found?
Ooh, that's a fantastic question. It opened up so many possibilities. Different puzzle pieces could lead to different thresholds, different strategies, a whole new set of challenges.
This whole deep dive has just sparked so much curiosity. It makes you wonder what other hidden patterns and thresholds are out there just waiting to be discovered.
It's a great reminder that in math, even a simple concept like tiling can lead to these incredibly deep and complex questions. There's always something new to explore.
Couldn't agree more. And for our listeners who want to really dive into the nitty-gritty details of Gomez, Leos, and Martin's work, we highly recommend checking out their full paper. It's definitely challenging, but it's packed with insights.
Yeah, it's a tough but rewarding read. If you really want to understand all the nuances of how they achieved this incredible result, it's definitely worth the effort.
Well, thanks for joining us on this deep dive, everyone. We hope you've enjoyed exploring the world of randomly perturbed graphs with us. Until next time, keep those mathematical gears turning.